and we do AC. AC and DC. Okay. DC, I think no issue, right? AC. Okay. First is we talk about mathematical modeling. Okay.
Huh?
If I teach the same way your teacher teach, you have the same questions. We talk about mathematical modeling. Okay.
Mathematical.
Mathematical modeling. Just English. I'm talking about English. Okay, not any cheaper. Okay. So if you have something that is fluctuating, okay, sinusoidally, how to model these things in maths. But if I have this to be, let's say, how to have an equation for this? The idea is that if I have this, is let's say I want a k minus k height, but this axis, right, is in terms of, let's say, okay, time. Okay, of course, in us is time. Okay. The first thing is that we can model this by saying that this quantity q. Okay, this quantity is in terms of time. Okay.
Mm-hmm.
Okay. Yep. So equal to what? Okay. It is very tempting to see this thing I'm modeling use sine functions. Okay. Sine t. Okay. But then I have a lot of problems. Okay. The first problem is that can I change this? Can I change this to other thing? Cannot, because it's about q to t. So this is fixed. So how to model these things that I want to model? Okay. The first thing is the sine function is kept between plus and minus 1. But it is plus and minus k here. Okay. So therefore, I time k will be able to plus minus k. Okay, so this is set. Okay. The second problem is that the sine inside cannot take time. Sine function inside is taking an angle. Right? Got to be an angle. Okay, but it may not have an angle. So this is why, right, it's not allowed to use a t. So how to abuse the sine functions that I can model in my situation is that you need a theta and t mapping. The t is the actual quantity, it's in terms of time. But I need to make it a theta so that I can put inside this function and abuse it and use it. Okay? So what's the best way to map these things? Now, by the way, right, this is what called a phase angle. Okay? When in wave, in any chapter, right, the phase angle is actually an angle that representing a time. Okay, in the period, and it's not really a time because you see this angle is between 0 and 360. After that, you go back to 0 to 360 again. It's in a rotating manner. Okay, so it's actually tell you that it is a periodical instant, a specific instant in a periodical motion. Okay, so this kind of virtual angle, the angle that for the sake of mapping is what we call the phase angle or the phase. The phase angle, they're the same thing. Phase. Okay, so angular frequency we call the phase frequency is the frequency of this phase. In the circular motion, so nice that this phase angle is the same as the physical angle. Horizontal motion, say when the phase go 90 degree, the phase of one complete cycle go 90 degree. Your physical angle will go 90 degree. Okay, so therefore in that case you can abuse the phase angle as a physical angle, but not in any other things. For example, vertical circular motion, you cannot say this phase angle is a physical angle. Because time go up and down a little bit different at every point. Okay, so when the phase go 90 degree, 1/4 of the motion, it may not be the physical 1/4 of the motion, because speed going up arc and down arc are different. Okay, whatever it is a phase angle for the sake of putting it here. So how to do the mapping? The mapping is that the easiest way is to do a linear mapping. Okay, is they say that okay, one cycle the time is t. Okay, and one cycle the angle is 2 pi. Okay, so therefore the t is the theta. Therefore the theta is equal to 2 pi over t.
Huh? How is it t over theta? The unit is it?
No, it's like it's a linear mapping. Okay, now.
What is linear mapping?
Okay, for example, I say $2 per plate of chicken rice. So number of plate of chicken rice, $. Okay, how to form equations. I say, okay, $2 for one plate of chicken rice is equal to the dollar to the chicken rice. Okay, therefore I will have the equations like if I have one number of plate of chicken rice equal to $1 divided by 2. Okay, so give $2, 2 divided by 2 will give you one plate of chicken rice. Okay, this is a linear ratio.
Oh.
Yeah, okay, it's a very fundamental things of maths. The direct proportion. Okay, so same thing here. How do I want to map? Have a linear mapping between variables t and theta. Okay, I just put in a specific value of the period. For one period for time in the angle I wanted to linearly map to 2 pi. Okay, so period to 2 pi, 360 degree. Okay, is equal to any time with any theta.
Oh wow.
Got it? Okay, so this how we can get this. Okay, therefore you will arrange, you have this. Okay, therefore that we name this 2 pi over t, right, as actually a constant that can map a t to any theta. Okay, so therefore they call it omega, and they call it angular frequency or angular velocity, and the so-called angular is above phase angle. Okay, so this is called omega t. So omega t is equivalent with the theta. Okay, so therefore you put omega t back to here, it will make sense. So how do you model this waveform? You model this waveform with this is equal to k sine theta omega t, and omega is 2 pi over period t. Okay, your problem about this is it?
You don't need to explain that, right? I just know 2 pi over t is omega.
Yeah, but if you learn this, right, you will be able to formulate any formula for any instance for you. From there, you can do differentiation integration. The simple harmonic motion at time, you use it. Wave, you use it again. AC, you use it also. So if you learn one here, right, you learn 3. But if you don't learn this one here, you're going to learn separate 3. Okay, so mathematical modeling is just like, I want to model this kind of pattern, and that's the way I model it. Okay, why omega? Because this can contain angle. Okay, so I use this to transform this t with become the angle theta. Okay, so this one omega t inside. Yk because the sign is kept plus minus 1. And how to find omega? Omega is 2 pi over t. Why omega is 2 pi over t? Is because of the linear mapping. Okay. Okay. Another illustration of linear mapping is gradient. Okay. How we find the equation of the line pass through the point, let's say 1, 2, and 3, 4. Okay. We say 4 minus 2 over 3 minus 1 equal to y minus 1 over x minus y minus 3 over x minus 1, y minus 2 over x minus 1, right? Okay, remember it? Okay. Actually, what is this? You're using saying this is 3 minus 2 is 2, 3 minus 1 is 2. Okay. So actually say 2 over 2, right? Is equal to change in y over change in x. Right? Same thing. Okay. I use this ratio, which is a ratio of 2 quantities, to keep me a relationship. So I have period with 2 pi mapped with any generic time and theta. This is linear mapping. Okay, so you don't understand the chicken rice, you can understand this. Okay. Okay.
Yeah.
Now this pattern you must learn. Okay, a lot of things will come in this technique. Okay. If they tell you pressure increase, your temperature increase. Okay. If they say the
pressure or temperature.
yeah, So you say P1 T1 equal to P2 T2. Right? Linear mapping, right?
Oh, but this P1 and T1 is like full numbers.
Yes, but this can be a generic number, right?
Yeah.
Okay, so like that, right? So therefore, right, if I say T is mapped to angle, a time is mapped to angle. So I say period mapped to 2 pi is the same as any time with any degree. Okay, so therefore that's what we call the linear mapping. This is what we call the linear mapping also. Okay, so therefore you have the theta is what we put inside the sine function is equal to 2 pi over t times t. So, and we call this omega. What's the use of this? With this omega, you time whatever second, how many seconds, it will give you better angle, how many radian that you put inside these functions. They will fluctuate together with this. Now, what's so good about modeling these things? Okay, so in short, you just need to remember the modeling formula, which is the sine, cosine, whatever omega t. Okay, so in AC, maybe V or A, right? Okay, so V are with fluctuating with time. Let's say this AC is the AC is the AC the voltage, right, is fluctuating plus minus of.
Isn't
3.
AC like the current like go this direction once and go this direction once but
No.
change very fast?
No.
The current.
First things right about a current, okay? A current, right, you do not think about an electron move from here to here. No. Don't think this way. A current must think in electron congested, not compressible, like water like that. When you have one in, you have one out at this instant.
Yeah.
Okay, so the current high or low, right, tells you how much go here, how much come back here.
So what's the like cycle?
The idea, yeah,
What's
it's,
like,
it's the whole thing.
It's like a wheel then turn.
Yes, you're right. So it's like the first one maybe turn a bit, then turn a lot, and then turn a lot more, turn a little bit, don't turn another bit, turn a bit, turn more, turn like that.
Oh.
Okay, so that is the AC current thinking. Okay, but let's model. So why do I bother about modeling? Okay, because once you know modeling, right, you know any instance, you substitute the time at any instant. I know that any times the voltage, the V. So let's say this is 3 like that, and every cycles they take let's say 4 seconds. And that means the frequency is 1/4 means 0.25 hertz. Okay, this kind of V, right? Okay, so you can model it in this way. Okay, so what do I have? I have
It's the
3
peak one.
minus 3, okay,
Oh, peak is not.
and it is 4 seconds, right? So this V equations, the V at any time you're happy with, right, is equal to 3 sine 2 pi over 4 t. Okay. So can I find it is what happened here? It is 0.27 second. What's the value here?
3 sine 2 pi over 4 times 0.27.
Yep, you just substitute this is 0.27 second. You press the calculator, you get at the instant what's the voltage. Okay, so now
Is
once
this
you
formula in the booklet?
Yeah.
is it? I don't know.
Yeah.
But the modeling of this, right, is useful here in a wave and whatsoever. Okay, many chapters. Model it, right, you can do a lot of things. For example, so what's power? Power at any instant is any instance V times any instance I, right? So then you have the 2 sine function go inside, then the 2 sine become sine square, that kind of things. You sine square and then change something, you get some form. On the other hand, right, they say if this is speed, okay, let's say simple power motion, the speed fluctuating, okay, and then you find acceleration. How do you find? Differentiate. Differentiate with respect to t, right? These things take out and all these things, right? You still have a lot of things to do. So modeling is important. Okay. So the first thing is that this is the way to find any instance v. Okay, so when any instance v square, you can do this one square also. Over r, v square over r equal to power, then you can get r also. So the power is in sine square graph. Okay, so in the end, all you need to know is this. If v, right, is start with v naught sine omega t, okay, then the I, right, will be in the same phase, okay, will be I naught sine omega t. Why? Why must this guy be sine, this guy must also be sine? Okay, the reasons, right, is due to the what law? Ohm's law. Very stupid, Ohm's law. Ohm's law say v equal to IR. Okay, so I and V are related with the constant R, and the resistance of the resistor is never fluctuate. It's a constant. So this is why if V equal to V naught sine omega t, your I, right, is equal to V over R, right? Okay, it's equal to V naught sine omega t over R. Okay, therefore you know this actually V naught over R sine omega t. The idea is that if this guy is in omega t, sine omega t, this guy is also in sine omega t. So it's guaranteed that in normal AC, right, that V and I are in the same phase. Okay. So secondly, of course, okay, if you want to talk about I naught from this equation, I naught is equal to V naught over R. Okay. This guy's not. This guy's not.
So voltage increase, current increase.
Yeah.
It's like when voltage is at 70% of its potential, then current is also 70% of its
You're right.
highest point.
They're the same. Okay. Same phase.
Okay.
Okay. And the value you can just deduce. You want a max of I, you just get a max of V over R. Okay. So because of this, right? Take a look at this. Interesting. Talk about power. Okay. Power, right, is equal to VI. So power at any time, right, is equal to V naught sine omega t time I naught sine omega t. Okay. Therefore, it's V naught I naught sine square omega t. Okay. So power naught V naught I naught, right? Because sine is kept with 1 plus minus 1. And when you square it, right, it's worse, it's 1 and 0. They don't even have minus. So the max is 1, so the max is 1 is P naught equal V naught I naught. Got it? Okay? And so, but the interesting thing is that you got to see this graph, okay? Sine square graph is very interesting from the calculations, from the graph, okay? Now, so if V, right, is a sine graph in this way. Okay, let's have 2 cycles. So what happened to power? Power is a sine square graph. Okay, sine square graph, right? Okay, is actually you can step it to a cosine formula. 1 minus 2 sine square theta. Okay, so we bring it over 1 minus cosine 2 theta divided by 2. So it's half minus half of cosine square theta. Now, this is interesting. When you have center line, and you plus half, right, shift the center line up by half. Okay? Then on this shifted line, right, half shifted line, you draw a cosine square, you draw a cosine 2 theta graph. That means draw a cosine graph. Okay? Cosine graph means you start with the top here and then to the bottom here. But do I go through it or something? The amplitude is half. Okay? So half means plus half and minus half. Yep, so kind of things like that. That's why it touch. Okay? So you see this. And I think I did something wrong. It's a minus. So it's a flip. So it start from here. Okay? So this one is correct. So what do we have? Okay? But one more thing is that it will be 2 theta. 2 theta means the thing is
squeezed.
squeezed. So how will it look like? We start with 0 here, and now this is, if this is a plus minus 1, right? This is plus minus half. So we'll be at half here, but then we start with here, so it will be 50. So we go, this is one cycle. So now I need, this is one cycle. So go up here and go up here, down here. This is one cycle. So up here, good, down here, up here, and down here, and up here, down here, and up here, down here, different things. Okay, and the height will be different because you still have this knot and this knot. Okay, so maybe taller than that. But the idea is that from an up-down graph, it become shifted one side. It's different from the absolute value. Absolute value you see sharp corner, but no, actually it is a cosine. Okay, so this is a turning point also. Okay, anyway, it's your GC. You can see the actual shape of your. So how the power fluctuate? It fluctuate this way. Okay, so we have two things. First thing is the peak value, okay, and the instantaneous value. Then the last one we talk about is the mean value, okay.
Of current or power?
Everything, current, power, and voltage. Now, the mean value, right, of this kind of quantity, you have problem, because if you take the x, right, direct mean, right, it's always 0.
Huh? Oh,
sense?
yeah, they cancel out.
Yeah, they cancel off. Positive and negative values. Always you add it up and average is cancelled off. So I want to find the average value. How do I find? If we give you a lot of points.
Average value of the positive side, is it?
Yeah. So the first issue is that you don't want them to be negative, so they will cancel the positive. I want to have average value. So this one, if I give you all the x, right, you try to have the x squared something out, and then divide by the number of points you have, or the x. Square it so that you don't have any negative. Okay? So average it, because how many points divide by how many points get the average value of the point. But of course you square it, you make the magnitude bigger, so you take back the square root. Okay? And that's the only thing you can do. Because if you don't square it, it will have positive and negative. Then you can't get any value. If you square it and square root it, then you actually using absolute value. Okay, but that you cannot do the absolute value last time. Okay, so they have this.
This x is the what x, the what square?
Is all the points values.
Every value square.
Every values, yeah. Look at the average. Yes, and then divide by n, average it. But I want to get a close value, so I take back the square root. This tells you what is the meaning of root mean square. Root mean square is trying to make average. Okay, but because they are vector, so they get cancelled. You can't just use a direct average. And last time they don't have absolute value in the calculator, so square it first, average it, then you square root it back. So this is a root mean square. Root of the mean square, average of square, a root mean square. So now if you understand what's a root mean square, right? Okay, I jump straight to the point to tell you how to calculate a root mean square of any shape. The root mean square, of course, is indicated as root mean square. Okay, so let's talk about DC. Okay, the DC, right? Actually, you have so how to say this? Let's say it's 4 like that. Okay, so all these points are 4. How many points do you have? Of course, infinite number of points. Okay, so infinite number of points. I don't know. Okay, but let's call it. I have n point. N is very large. Okay, n point of 4. So you talk about the root mean square values, this is v. So v root mean square will equal to square root of the mean of all the square, right? So how many points I have is n so many, and each one is 4 square.
Yeah.
Right? We're correct? Okay.
But the n and the n on top cancel.
Yep.
If it's already positive, do we still need to do the square root and square?
Yeah, we don't have to, but the point is that we need to use one formula for everything. Okay, so this case 1 only. Okay, so how many 4 are there? N so many, right? Divide by the n, you get 4 square, so 4 square square root, you get 4. So this is why, right, for DC, this is the root mean square value. Okay? So let's try the, how about the root mean square value for minus number?
You just
Same.
4.
Negative 4 squared.
Negative 4, 4.
4.
4, right?
Yeah, because it's square, you can positive.
Yeah.
You cannot go back to negative.
So this one is 4. Okay, so this is how we do root mean square.
DC, then you can do the
Right.
AC.
Yeah, of course, okay. Then now we do AC. Okay, then later we will combine them.
Well, combine on that.
Well, let's try, okay. Let's do some very good waveform so that you understand what I want to teach. Anyway, now for AC, right, the accuracy of this argument is minimum is a repeating cycle of 1/4 of a complete sine cosine wave. That means anything is a multiple of 1/4 of wave. This is correct. Okay, you can use this formula.
Minimum 1/4.
Minimum 1/4. 1/8 cannot.
1/3 can.
1/3 cannot.
1/3 is more than 1/4.
Yeah, multiple 1/4.
Oh, so it's like
Multiple.
1/4 half.
Half or 3/4, that kind of things. Okay, it all makes sense. Okay, the first thing is that, okay, so let's teach you the small one, okay, detail. Okay, so let's have like things like that, and then we have 4 minus 4. Okay, in one cycle, let's talk about one cycle first. So what is the V root mean square value?
2.
Cool. Yeah, I know, you know, not 2 what? It's 4 divided by root 2, right? It's 2 root 2. 2 root 2, yeah. Okay, so let's try, okay. So how to come up with this is that root mean square is equal to square
You need to
And
take
let's
two
say-
values, right?
n of it.
But why do you assume n to be 2?
N to be 2. No, n is many points here.
Then how do you get root 2?
Oh, yeah. This is how we get it. Okay. So this is a definition of root mean square, right? Good. I need to add all the squares there.
4 square. So it's like a lot of 16s.
Isn't it like v not root mean square? Just the maximum.
We don't root mean square.
Because you're only taking the maximum point, right? Then we have
Root
2
square.
points, then we root 2.
You don't know the
Oh
middle,
yeah,
right?
we don't do that. Sorry. We don't do that. Okay. I'm not going to teach you so detailed. Or should I? Anyway. Root mean square is equal to V naught over square root 2. Okay? That's actually from the
Only the v
from
naught.
the integrations. From the integrations. Okay, how do they do it? Okay, never mind. This one is not needed. Okay, I'll just show you. Okay, so let's say this is 4 minus 4. Okay, so
What is V naught?
Maximum.
maximum.
Oh.
Okay, the maximum in this case is 4. So put in 4 equals square root 2. So root 2 root 2. Okay, in this case. Okay. Anyway, how do we come up with this formula? Right, is that the V is modeled with V naught sine theta, sine omega t. Okay. So the idea is that you want a root mean square. That means you want square root of n and sum of n, sum of v square, sum of vt square. Can? Can. So the idea is that how I'm gonna get the how we get this
Sin square omega t is 1, is it?
sine square omega t.
Wait.
No, it not
No.
sine square omega t will not be 1. Okay. Anyway, and then what is this? Okay, this means, right, summation of v square of dt through a cycle. Okay.
What is that an integrate?
Yeah, because it's a sum. This is actually a sum. where delta x delta t tends to 0. Okay, so therefore you have a integration of v naught sine omega t dt. Okay. Okay, so this is divided by the period. Okay, this is the period. V naught take out. Okay, integrate of sine. Integrate sine is what?
Negative cosine.
Negative cosine 1 over omega, right?
So this is only one cycle.
Yeah. They use of one cycle divided by the time of one cycle. Okay.
If it's just one cycle, we only have one V naught.
Sorry? We just one cycle we only have.
One V naught. Then
Yeah, no, this is the functions fluctuate throughout everything, right? So you integrate all this point means you integrate everything, right? That means you add up all this point, right?
but you're only considering one period, is it?
Yeah, in one period. So this one we divide by the t. So this one you integrate and only until one period.
Okay.
Okay. So what did I get? Oh, I'm wrong. The square is a square. And then sorry, I work it out for you next time. Okay, or maybe I just send email to you. Okay, this is a bit complicated. Cosine square. Okay, what I want to say here is not to prove to you. I just want to tell you this. Okay, we know VRMS equal to V naught over 2. Okay, the average what mean square value, R over 2. So what if you have a waveform like that? Okay, so let's say this is 4, this is let's say minus 4.
No curve at the negative region.
There is 1, 2, 3, 4, yeah, no curve in the region. Okay, so keep going this kind of pulse, right? How to get RMS value. Okay, the idea is that, okay,
Still need square, huh?
sorry?
Don't need square, is it?
Don't need square, okay, you just find the root mean square. Okay, so remember, right, this is a multiple of 1/4 of the cycle, so you can use this piece of information. Okay, so the idea is that you want to find the root mean
Find this
square.
number then divide by 2.
Find this number divided by 2.
Huh?
Because the pulse is like 50% of the time got stuff on.
Is that like that? Let's try, okay? Root mean square, this is the ultimate method, okay? Equal to all of them, okay? And you try to make it 2 portions, so what do I say? There are 2n there. Okay, 2n. Okay,
You are doing the first 50%.
we'll do it everything together.
2n.
Yeah, 2n, okay?
Oh yeah.
2n's number of points there,
Okay.
okay? So the behind sign, right, is n so many of minus 4.
But this don't have anything.
Minus 4 here.
Oh, it's one straight line.
One straight line, yeah.
Oh,
Okay, so pulse like that, okay? So this is okay, right? So
Yeah.
all you need is the thing in front, okay? So the idea is that I need the V1 square, V2 square, until Vn square, okay, for the first arc, okay? So how to do the arc? Take out the arc, reconsider it.
Then you do is the
Yeah, use
formula.
this. At this arc, right, the RMS equal to V naught over square root 2, so equal to 4 over square root 2, so equal to 2 root 2 for this arc only, okay? But this arc, right, is equal to its own RMS, so there's n point, since I have n point here, and it's a V1 square plus all over the Vn square, right? Okay? So that means, right, you can rewrite this equation by 8n.
Why 8n? You square both sides.
Yep, square both sides times the n over. Can you see it? Use this, square it, you get 8 times n, you get this. So
No.
you keep this side here. So these things, right, can be substituted back to here. So what do you have? So this is actually 32 over 2. 16 over 2 equal to 4.
Wow, so complicated.
Yep. No, I'm just trying to elaborate to you.
Then
Any kind of waveform, you can always break it down in, use this ultimate way to find the true RMS for it.
so the V naught is 16.
V naught is
Eh,
16. V naught is
eh,
4.
no.
The VRMS that thing right can only be done when the thing is
Yeah, this is only for
sinusoidal.
sinusoidal.
Okay.
And in the accuracy of 1/4.
Okay.
1/4 is this amount, half is this amount, 3/4 is this amount, full also this amount, same thing.
Okay.
Okay? That's the way to find it. Okay, so let's try, I give you one, see whether you can do it. Now if you have a waveform,